Now we will talk about how we can determine the presence of antiferromagnetic order in a material. The first obvious choice is to try to see it using X-ray diffraction. So let's talk about what information we get with X-ray diffraction. Well, the problem is using X-ray diffraction. We can only get our information about the positions of the atoms. And why is that the case? Because we need to look at the interaction mechanism. The X-rays, when they penetrate the crystal, they're basically interacting with the electron clouds around the atoms. So we can see the scattering of the X-rays due to the interaction with the electron clouds. So this is giving information about atomic positions since X-rays interact with electron clouds around atoms. So what is the alternative for X-ray diffraction? The alternative is using neutron diffraction. And the advantage is that the neutrons carry magnetic moment with them, so they're also scattered by the magnetic moments of the atoms. Therefore, the information we get from the neutron diffraction is also sensitive to the magnetic order in the crystal. So the choice is, however, neutrons carry magnetic moment the magnetic moment of a neutron is of the order of 10 to minus 27 ampere meter square, about 4 orders of magnitude, 3 to 4 orders of magnitude less than a Bohr magneton. So they are also scattered by magnetic moments of the atoms. Now, the principle of diffraction is basically based on the principle of Bragg, that is Bragg diffraction. And in Bragg diffraction, we have parallel planes of atoms, atomic planes. So these atomic planes are interacting with the incoming X-rays, and due to the interaction with the electron clouds, given that the distance between two adjacent atomic planes is d, if we drop a perpendicular to the path of the incoming and reflected X-rays, you can see that if this is the angle theta for the incoming X-ray, this angle is going to be also theta here, so it's the same angle theta here. So if you have a 90-degree angle, then this angle is also going to be, most important angle here is this angle. That angle is also going to be theta. So you can see that we have a triangle here. The hypotenuse is d, and the extra distance the atoms, the X-rays are traveling when they are reflecting from the atomic planes is this distance, the one I show with green. So when the X-rays are coming, they are coming in phase up until the point, so we have them parallel here, up until this point, and then the X-rays that are reflected from the bottom plane are traveling an extra distance, a path distance. So if you look at the interference of these two X-rays that are reflected, so we're going to concentrate on the interference of these two rays on our detector. So for constructive interference, the condition is the path difference between the two, delta path difference, must be equal to an integer multiple of wavelengths. And how much is that path difference? You can see that we have two sides of the triangle here. So this is going to be, so let's show this with blue. This side is d sine theta, and this side is also d sine theta, because you have the same angle theta here. This angle is also theta, and therefore we find that the total path difference is 2d sine theta. So 2d sine theta must be equal to n lambda for constructive interference. So d is the distance between adjacent atomic planes. Theta is the angle, incidence angle with respect to the plane. N is an integer, lambda is the wavelength, and delta is the path difference. So if you look at, for example, in a body-centered cubic cell, in the body-centered cubic structure, when I draw the planes, the parallel planes, for example, I have the 001 plane, 002 plane, 001 plane, etc. So this is the family of 001 planes. You can see that because there is an interpenetrating plane that is established by these body-centered atoms at the body center, so they are creating this plane. When I look at the path differences created here, here I have one situation, and here I have another situation. So if I look at the interference of these rays, I will find that there will be destructive interference coming from the 002 planes. So for the family of 100 planes, so due to symmetry these planes are all equivalent. For these planes to give constructive interference, the path difference between reflected and incident waves must be an integer multiple of lambda. And from similar triangles, you can see that the plane number 2, that's the body center, gives a path difference of n lambda over 2 path difference. So there is no 100 diffraction line. So the intensity is killed by reflections, creating destructive interference from the body, the planes created by the atoms at the body center. However, if this is an antiferromagnet, what would happen? If it's an antiferromagnet, we can, for example, put one sublattice consisting of magnetic moments pointing like this, and then you would have the magnetic moments of the body center pointing in the opposite direction. So using X-ray diffraction, you would see no effect of the magnetic moments. However, if the magnetic moments on plane 2 have a different orientation, the scattering amplitude would be different for neutron scattering, because the neutrons are interacting with the atomic magnetic moments. So if you look at this structure and you see the appearance of diffraction peaks, so the appearance of diffraction peaks below the Néel temperature, below Tn, this would be direct evidence in a BCC structure to antiferromagnetism. So, but this can only be done using neutron scattering. Another advantage of using neutrons is that neutrons can also distinguish adjacent elements in the periodic table. So if you have a different type of element in the body center, not just only having a different orientation of the magnetic moment, that can be distinguished using neutrons. And why is that? And it is through the dependence on Z, the atomic number. Now, typical values for the wavelength of neutrons, you can obtain 1.49 angstroms at room temperature with an energy of 0.01 electron volts. The mass of a neutron is 1.67 10 to minus 27 kilograms. So you can calculate that's for a 0.01 EV or 10 milli electron volt neutrons. That is roughly the wavelength that you obtain. So this would be, and that is angstrom scale wavelength is sufficient to distinguish the magnetic moments that are separated by orders by a distance of the order of atomic spacing, lattice constant, which is of the order of angstroms as well. Okay, so in summary, we talked about detection of antiferromagnetic order. We have learned that using X-ray diffraction it's not possible because the X-ray diffraction is based on the interaction of X-rays with the electron cloud. It's not sensitive to magnetic moments. However, if we do neutron diffraction, neutrons carry magnetic moments about 4 orders of magnitude, 3 to 4 orders of magnitude smaller than a Bohr magneton. However, because of this magnetic moment, they interact with the local moments and give information about the ordering of the moments. The diffraction principle is based on Bragg's law, 2d sine theta equals n lambda. So if you have rays that are scattered from two adjacent planes, we look at the path difference between the reflected waves from the two adjacent planes, and the interference pattern will be constructive. You will see a diffraction peak if 2d sine theta is equal to n lambda. For example, if we look at a body-centered cubic structure, the plane created by the atoms at the body center causes destructive interference with the planes adjacent to it. So you can see that in the Bragg diffraction in a body-centered cubic lattice. So regular X-ray diffraction would not give us any peaks or a very small intensity at these locations. However, if we do neutron scattering, and if this is an antiferromagnetically ordered crystal, we would see a different scattering amplitude for magnetic moments pointing in opposite directions. Therefore, the appearance of these diffraction peaks in neutron scattering would be direct evidence for antiferromagnetic ordering. And another advantage is neutrons can also distinguish adjacent elements. It has a Z dependence. And the typical wavelength of neutrons that you can use in neutron diffraction is 1.5 angstroms at room temperature for an energy of 0.01 electron volts, and the mass of a neutron is 1.67 10 to minus 27 kilograms. So you can check the energy by using free neutron energy h bar square k square over 2 times mass of a neutron.